Hello everyone, my name is Mohammed Ghazah, and I'm a physics and math student working under Dr. Gamir for my undergraduate research project. Today I'd like to talk about my project, which is on the magnetotransport study of gallium-doped thulium manganese 6 tin 6. So the family of compounds TmMn6Sn6, where R is a rare earth atom chosen from the highlighted elements in the table here, has gained much attention for hosting very unique magnetic structures. Because of the layered structure shown here, where the manganese layers are separated by two different blocks, one tin containing layer and the other tin and R atom containing layer. The magnetic interaction between the layers is different, as shown by the exchange constants J1, J2, and J3. The competition of these different interactions and the external magnetic field leads to a very unique phase diagram, and this is an example of the phase diagram with the rare earth element chosen to be yttrium, with magnetic field applied along the AB plane. Now choosing the rare earth element to be thulium, we have thulium manganese 6 tin 6, which was found to host a unique helical magnetic structure consisting of three spirals pointing along the z-axis. Thulium and manganese atoms are responsible for the magnetism in this material, and as a result, there is an additional interlayer interaction J4, shown in this schematic of the crystal structure, where the green spheres are thulium, black are manganese, and the rest are tin. Through gallium doping, tin atoms will be replaced, and due to their difference in sizes, gallium being smaller than tin, there will be a change in the magnetic interaction between the layers. Our goal is then to influence the spirals in the parent compound to create a magnetic structure that can be easily manipulated by just a small current density. Such magnetic structures are of interest and can be used in spin-based electronic devices. In my previous work, I synthesized single crystals of several concentrations of gallium doping and was able to measure the susceptibility, which is just a measure of how strong the moments are to get an idea of which direction the spins point. This measurement was done at 0.1 Tesla of magnetic field and along both directions, the AB plane shown in black and the z-axis shown in red. For the parent compound, we can see that the black line is continuously above the red line, indicating the moments are in the AB plane. With minimal gallium doping of x equals 0.2, we've drastically changed the trend, but the black line is still above the red line within the whole temperature range. However, now that we increase gallium doping to x equals 1.2, we see that there is a crossover temperature at which the red line is now above the black one. The same is seen for x equals 1.7 composition, except now the temperature at which this occurs at is greater. Such behavior is an indication of the spins reorienting from the AB plane to the z-axis. Thus, in this project, we were successful in manipulating the anisotropy of thulium manganese 6 tin 6 through gallium doping, and so I'm currently writing a paper on these results. The main objective of this project is to do a magnetotransport study of these compounds, which could reveal some indication of existing novel magnetic structures. The particular magnetic structure of interest is called the skyrmion, and its significance is in data storage or data processing, as it can be manipulated easily with a small current density. This structure forms only in this region for the compound manganese silicide. When electrons move through such a magnetic texture, the electrons pick up a quantum mechanical phase called the Berry phase, which acts as a fictitious magnetic field that deflects the electrons and gives rise to an additional Hall signal, called the topological Hall. A signal of this was observed in the data highlighted by the hump here. The magnetic structure must not necessarily be a skyrmion if this hump is visible, but it could also be a result of non-collinear or non-coplanar spin arrangements. Our goal is to design such textures and detect them by Hall measurements. In the Hall effect, current and magnetic field are applied in perpendicular directions in a sample, and due to the Lorentz force, a voltage is developed in the direction perpendicular to both the current and the magnetic field. In normal metals, the Hall resistivity, which is proportional to the Hall voltage, is linear with respect to the magnetic field applied. As I showed before, simply a deviation from the linear behavior indicates a topological origin, but care needs to be taken as this deviation could be a result of intrinsic ferromagnetism. So this is a sample I prepared which resembles the example figure with 6 electrical wires. So these 2 wires are for current, and these 2 pairs are for Hall purposes, while these 2 pairs are for MR purposes. This sample is then placed on a puck, which can be put into our physical property measurement system, which allows us to measure the desired values. So this is the data for the Hall resistivity with magnetic field applied along the C-axis of the crystal and the current flowing in the basal plane. So we see here the anomalous Hall effect, which is just the Hall effect occurring at zero magnetic field due to the ferromagnetism of this material. So the Hall follows the magnetism curve and shows a hysteresis loop at lower temperatures, but as we increase the temperature, this hysteresis loop disappears, as we expect from the previous magnetic measurements. So this data is interesting, but does not show any sign of novel magnetic textures. And so we studied the different direction. So this data is for one of my compositions measured in a different geometry, where the current is along the C-axis and the magnetic field is in the AB plane. So here I only show one particular temperature of 35 Kelvin, where we see a potentially interesting feature. So what we see here is the hump only appears within a certain range of magnetic field and is varying smoothly with the magnetic field. So we think this effect is a sign of topological Hall, similar to the one we discussed earlier, which turned out to be a skyrmion. And because of the length of time it takes to prepare and measure these samples, we're still completing more detailed measurements at the moment. So the plan is to do similar measurements on all other samples that I have prepared, and to confirm the nature of this magnetic structure, we need to do neutron diffraction experiments, which will hopefully be carried out in the near future. I also plan to present this work along with my previous magnetic study at 2023 annual APS March meeting. I'd like to thank my mentor Dr. Gmir and my peers Hari Bandari and Peter Sigfried for their assistance in and out of the lab. Thank you very much for your time.